Lovely. All right, so our problem today, we are looking at valid anagram. We're still in this category of arrays and hashing. Um, so we'll talk a little bit more about hashing today. We talked about hash sets yesterday. Um, so let's take a look. Before we get to the technical stuff, let's take a look at the problem. So valid anagram, it says given two strings, S and T, we want to return true if the two strings are anagrams of each other, and otherwise we'll return false. And then they clarify, in case you don't know what an anagram is, an anagram is a string that contains the exact same characters as another string, but the order of the characters can be different. And this includes like the frequency of the letters or the characters. So if one string has two R's and the other string only has one R, we would not consider that, or we would not consider those two strings to be anagrams. So they actually give us a couple of examples here. The first example, we've got string S is race car, and string T is car race. And these are, in fact, anagrams of each other. We'll diagram this a little bit in just a sec. But in short, if you go through each of the letters of R, you can find a corresponding letter in T, including the frequency. So that first R in race car, the R at the beginning and the R at the end both have an R that they get mapped to in the other string. Okay, example 2, we've got jar and jam, and these ones are not anagrams. So if you were to look for the J at the beginning in the other string, it is there. The A, it's there, but the R, we don't find it, as well as vice versa. The M in jam is not in the word jar, right? So in this case, we return false. And then they give us just a quick constraint here, which is that the two strings S and T are only ever going to have lowercase English letters, so we don't have to deal with like comparing capitalization or numbers or anything like that, just lowercase English letters. So let's diagram this a little bit. Similar to yesterday, we're going to go ahead and work through this as though we're doing it by hand and think about how we can code that, and then we'll come up with some optimizations. Oh, me when I scribble. Yeah, I'm gonna try out Figma here. I don't know if this is gonna work, to be honest with you guys, but we're just seeing, what format works best here. So, let's take a look at two strings. Does anybody have like an anagram they like? Oh, you know what's really like pop culture relevant right now? Oh, is this? Well, we're gonna go for it. Undertale. Okay, who knows what comes after this? Who knows what my corresponding anagram is? Anybody? If you're typing Deltarune, you are correct. Isn't that crazy how Toby Fox did that? Wild. Okay, anyways. So if we were trying to figure out, hey, are these two strings anagrams of each other? What we might do is we might look at one of these letters and search through the other string to see, did we find it, right? So if we do this sort of the long way, the by hand way, we have to look at each letter and say, is that the letter we're looking for? No. Is that the letter we're looking for? No. No, 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 no. And then we get to this U, and kind of the physical analog that we might use to keep track of this is we might then cross out this letter and say, this is no longer one that we can use. We just used it for the U, or for that first letter over here, so we can't use it anymore. In fact, let me do this a little bit more pointerly. So we've got that pointer up there, and then we've got another one over here that is tracking what we're comparing it to. We finally get over here to the U, and we say, hey, that's actually the letter that we're looking for, and we can now cross it out, or scribble it out, or whatever you want to think about it. Okay, and now that we've found that, we can take our pointer up here and we can say, let's look at the next letter. Okay, now we're looking for an N, and again, we would come down here and say, okay, let's start at the beginning of the string. Is that an N? No, 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 no. We don't need to look at this one anymore, but we can go over here. And eventually we realize, okay, this one is an N, just like the letter that we were looking for, and that means that we can scribble it out. Now, one thing that you might notice at this point is, well, how do we know that this is a letter that we should skip. In terms of the naive solution, what we might do here actually, like from a coding perspective, and we'll talk about other strategies for this, but we might literally just get rid of the letter. So as soon as we found a U over here, or let me think about how to do this. As soon as you found a U over here, we might actually just say, let's go ahead and get rid of all of that. It's not there anymore. We're going to remove it from the string so it doesn't, potentially get rechecked later on. Consider, for example, like the scenario where our original string was undertale with a U at the end of it. We don't want to look at this U and go, hey, you know what, we found another U. Because again, for anagrams, the frequency or the count matters. Okay, we'll talk about how to actually handle that in code in just a minute. For now, we'll just kind of magic it and say, hey, let's just assume that that's a power that we have or something that we can do. We could maybe use a hash set to see if that's something we've seen before. Anyways, okay, so I'm not going to go through the whole string here because that would take a really long time. Hopefully you can see by this point, if we were to go through all of the letters of the original string, we would find one that corresponded in the second string, and there would be nothing left over. Everything in the first string gets found exactly once in the second string. Just to go through the other scenarios, well, actually, let's say this first. Once we get through the entire first string, if we get all the way to the end of it and we haven't found any issues, we can then say, okay, we got all the way to the end and there were no problems. So this is correct. In fact, let's even go a step further than that. Let's say that there was an additional letter here at the end, like a Z. We would need some way to capture, hey, there were actually some leftover letters in the other. This is for day 2. This is, the title here is Valid Anagram, so day 2 of the Blind 75. Okay, so this is actually highlighting, I'm realizing as I'm explaining this, I'm not explaining it very well, because this is highlighting one issue, which is how do we keep track of the count of these things, right? It would be really nice if we had some mechanism to say, well, how many U's were there in the first string? How many N's were there in the first string? How many D's? How many E's? And I guess just to highlight this, if we went with the method that we just looked at a second ago, let's say there was like an S at the end here. If we were to get all the way through this first string and say, hey, I never encountered any issues, I found all of the letters of this first string and I got to the end, and then we returned true, that would actually not be correct, right? Because although we found all of the letters from the first string, we didn't, or that S in the second string was never matched up, which means that these are not anagrams, right? So in short, we want, and here's like a different by hand approach that we could take, is we want to be able to take each of these letters and say, here's how many times it happened. So that's not what I wanted. We might do something like this. We could say, hey, for the first letter U, that happens 1 time. For the second letter N, 1 time. And this one's not especially interesting because everything happens once, right? But we want to be able to capture all of these, and so this would go on and on and on. And for the other one, we would have kind of the same thing, just with the other letters. And we would get to the end, and this one has got an S at the end of it, right? Well, what we want to do is we want to be able to match all of these up to wherever they go, right? These guys all get matched up with each other. And we want to see, was there anything left over on either side? Were there extra letters here, or were there extra letters here, right? Okay, so this is one approach. We're actually going to talk about a couple of them. And let's talk about how we can do this effectively in code. We actually have a data structure that looks pretty much exactly like this. Hopefully, if you've been coding a little bit, this is like starting to look pretty familiar as far as like a data structure that you've used before. This is what's called in a few different languages something like a map or a dictionary, or sometimes just an object. JavaScript would just call this an object, although it has dictionaries too. What this allows us to do is it allows us to match up what we call a key with a value. You can think of the key as something that you can look up, much like a phone book. You can look up a person's name and it tells you the phone. Actually, do y'all know what phone books are still? Well, the concept of a phone book hopefully is not lost on you. You can look up somebody's name and it tells you the phone number that goes with it, right? Note, in this analogy, we wouldn't tend to look up a phone number to figure out which name it came from. That would be very difficult to do, right? Instead, we would usually look up someone's name and find the phone number that goes with it because there's some efficient way to find the name, right? Okay. So this pretty much is exactly what we're going to do. We'll talk about the way to do that in like the coding syntax in just a second. Yeah, in fact, I think we're just going to go for that right now. Let's take a look at how we can kind of code this up. And then actually, before we get there, the very last thing I want to say is we need some way at the end to check, was there something extra in the front or was there something extra in the back? In the first string or the second string, I should say. Okay. Yeah, let's go for it. Do I remember the syntax for making dictionaries in Python? I hope so. Okay, so here's what we're going to do. We're going to go through that first string letter by letter and produce a list that looks like this. It won't be a list though, it'll be a dictionary. So we're talking about something like for character in S. So for each letter in the first string S, we want to put something into a dictionary. And we could say something like, let's say sdict equals, is it just this? Pretty sure it's just that. Well, I guess we're going to find out. Okay, so for each character in S, what we'll do is we'll say, and here's our format for it. I'm going to write it out first. Ooh. Wow, actually, there's so much for us to talk about. Let's think about it this way. When we start doing this, let me write it down over here. When we start doing this, here's sdict over here, there's nothing in it, right? It's totally empty. And so if you were to say, okay, I'm going to add one to the letter that I'm looking for, well, the letter's not here yet. So there's a few ways we can handle this code-wise. We could say something like, and I'll again write it out here. If the character's already there, then we can just increase it by 1, right? And I'll just leave a comment there. Increase the count by 1. And if it's not there, then what we can do is we can say, well, it wasn't there before. Let me go ahead and just set the count to 1. Okay, so this is one way that we could code it out. We could say if car in sdict, and here's our syntax for how to reference the value as well as increase it. We can say sdict car equals whatever it was before plus 1. And alternatively, if it's not there yet, we can just go ahead and say, okay, add the entry then and set its count equal to 1. So that's what the keys and the values here refer to. If we, instead of saying key value, what we could say is, here's the letter that I'm looking at, and here's the count that it goes with. Right, so when we start this, we would say, hey, let's go ahead and set use count equal to 1. Okay, and that's this right here. This is, we've never seen u before. Go ahead and set it to 1. And if we have seen u before, then take whatever its count was before and increase it by 1. And yeah, we'll do that for both strings here. Well, before we do that, let's go ahead and talk about one way that we can improve this. Python actually has a great shorthand for writing this scenario, which is like, if it's not there yet, go ahead and add it in, or use this value if it's not there yet. We can say, hey, go ahead and add this entry to the dictionary. We can use this format get with the key, which is the letter that we're looking at. And then the second value that goes into this get function is a default value. Okay, so what this is saying is I want to set a value in the dictionary that goes with this letter. go ahead and get what the current value is, and if you don't find it, use 0 as this number. Okay. So if it's not there, we'll use 0, and 0 plus 1 obviously is 1. If it is there, go ahead and use the value that was there. So if we've seen a letter 5 times, for example, then we would change this to 6. And so this section, or this line right here, effectively replaces the next section. We can say, hey, go ahead and build the dictionary. Every time you see a letter, if you've seen it before, increase the count by 1. If you haven't seen it before, assume that we start from 0, basically. Okay, and we'll do the same thing over here. So for each character in the string t, we'll do the same thing. We also need a tdict to store this stuff. And we'll do the same thing. Tdict character equals tdict.get character 0 plus 1. Okay. Somebody's typing. I don't know who it is because streamer mode is cutting off your username. Okay, so this forms 2 dictionaries where we get the letters and the counts that go with them. And let's actually take a second, because we haven't done this yet. I just want to go ahead and print these dictionaries. This can be a good diagnostic tool for you to see, like, is this doing the thing I expect it to do? I actually don't know if I've got this syntax right, so I'm going to go ahead and check that real quick. And this will also help us to check if we... okay, great. This is just saying you didn't return anything. The type annotation says you should have returned a Boolean. We don't need to worry about that yet. And let's see if this did the thing it wanted us to do. You can see we've got R 2 times, which is correct for race car. We got A 2 times, also correct. C 2 times, and E 1 time. So this is effectively the thing that we wrote down on the diagram, right? And you can see the second one is the same thing, just in a different order. I believe Python, it preserves the order of insertion, and what that means is if you see a C first, C will be the first element in the dictionary. And you can see that that actually holds for the rest of this as well. C, A, R, and then it's not till the very end that we see E, and that's why E is at the end. Or E is the last letter for us to see. Okay, and so you can see these are doing the things that we want them to do. I believe in Python, we can actually do this to basically say, are all of the key value pairs the same in both dictionaries? So Python kind of gives that comparison to us for free. If we were not doing this with dictionaries, we would have a very hard time, for example, if we had a list of 2 things, trying to figure out how they worked together with each other. Let's just see if this works. And it sure does for these cases, and let's check for the test cases in general, and it works out. Okay, some extra things we can do for this problem. I'm actually just going to speed us along here because that took longer than I thought it would. We can actually do a check at the beginning. So notice if we've got 2 strings of different lengths, they can't be anagrams because there's no way for the letters here to hit all the letters here, right? So one thing we can start with is actually if the length of the 2 strings is not the same, let's not even bother doing the algorithm. Let's just go ahead and return false. Right? And then assuming that the lengths were the same, then we do a little bit more investigation and eventually return whether or not those 2 like tally dictionaries were the same, right? Okay, but there's other ways for us to do this. Let's talk about time complexity very briefly. If we go through the code here, this is like a quick check that we can do on lengths. We make a couple dictionaries. We go through each of the letters in string S once here, and we go through each of the letters in string T once here. So this is looking like linear time complexity, or O of n, just because we have to look at everything a constant number of times. For each letter, a constant number of times. Okay, and then at the end, we have to do a little bit of comparison on the 2 dictionaries that get formed. This is actually, I would say generally, this is what we call constant time complexity. And this is because at most there will be 26 entries in this dictionary, right? One for each of the lowercase letters of the English language. So overall, this is what we might call linear time complexity. It's fairly simple code, but there's actually alternative methods that we can do to solve the problem. Any questions on this approach though so far? Anything I can like clarify, explain, or anything like that? All good. Great. Somebody the same. Okay, great. I love that profile picture, by the way. I love pill-shaped dog. You know haunts? It's like haunts, but for dogs. Okay, some alternative solutions that we can use. Here's one that's really simple. Um, if we were to start by sorting these letters, they would naturally be able to, like, we would naturally be able to compare one by one each of the letters. Or if we just sorted the letters themselves, we could just compare the strings against each other to see if they're the same. So if you had two inputs that were anagrams of each other when we sorted them, they would be identical, right? So another way we can solve this problem is we can say something like return whether or not the sorted version of S is the same as the sorted version of T. Very simple, one line. In terms of time complexity, for technical interviews, we tend to say that sorting is going to take O of n log n. It's a little bit slower than just looking at everything a constant number of times, or each item a constant number of times. It does work, in theory, a tiny bit slower. If this is for very short strings, sorting is quite quick. It doesn't take super long. And so this might be a much preferred solution just because it's elegant and it might not, in practice, be very slow. Okay, was there one more solution I had in mind? Maybe. Oh, I wanted to talk about, no, actually that's about it. We have 5 minutes left, but I don't have much else to talk about, so we might call it there.